to our Institute for Quantum Studies seminar. We're very happy to have Long come visit us today. Long did his studies at the University of Texas at Dallas, and then went on to the Joint Quantum Institute at the University of Maryland. Following that, he went to go do his postdoc at the University of California, Berkeley, with Irfan Siddiqui, and we had a number of collaborations that have been quite productive and very interesting. Today, he'll tell us about the frontier and what's next for superconducting quantum technologies. So, Long, we're very happy to have you with us. Please tell us about your work.
Yeah, thank you very much for hosting me. So, as you know, much effort across multiple disciplines, physics, computer science, and quantum engineering have brought us to the era of quantum discovery, where we harness the ability to manipulate otherwise isolated quantum bits and also to construct sophisticated devices from them. In addition, we have started to explore new physics and quantum applications. For example, here I show some, results. Recently, people have realized topological phase transitions, discrete time crystal, quantum phase transition using intermediate scale quantum processor. However, it is not clear if we can have quantum advantage by just doing, this type of physics. And it has been argued time and again that we need a fault-tolerant quantum error correction. And the gist of it is that we, instead of encoding quantum information into one physical qubit, we encode the information using many physical qubits, and we call this the logical qubits. Now, the caveat is that we need a physical error to be smaller than the threshold error in order to reduce the logical error. And actually, if we do not do it well, as you see, if we do not correct the errors, then the error become more and more as we scale up and as we run the circuit. However, if we do a good job and we can correct the errors, and when the physical error on average is lower than the threshold error, then we have the break even, and we have lower error in the physical qubit, in the logical qubit compared to the physical qubits. And here is the state of the art using the service code. As you see, although Google has announced that for the equal to 5 distance, we have lower error, the error actually doesn't match the expectation from theoretical predictions, and that means we are actually not there yet. So why? If you look at Google's quantum architecture, you can see that it is very complex and the coherence is low. So no wonder that we have not arrived at scheduled quantum error corrections. So I believe that we should start from the ground and improve, all of the bits, all of these interactions in order to build a better quantum architecture. So today I would like to introduce you to the world of superconducting qubits, and I will discuss robust operations between, high coherence qubits. Much of that was done with Andrew Jordan here and his team, and I will also discuss better qubits and how to build them from the ground up. And the goal is to build a robust and resource-efficient quantum processor. Okay. So now the first thing we think about when we think about quantum mechanics is atoms, because in this atom, there's only one single degree of freedom. This is isolated from all of the noise processes. So how come this circuit can act as a quantum object? Well, the key here is that if we put this circuit in a superconducting state, such that all of the electrons form Cooper pairs, and these Cooper pairs can be described as a single condensate, then there remains only 1 degree of freedom in this circuit. So then the dynamics of this circuit is completely analogous to the dynamics of the hydrogen atoms. Here, instead of the dynamic of the electron, we have the dynamic of the condensate. Instead of the velocity of the electron, we have the current running through the inductor, so on and so forth. But the advantage and the difference here is that this atom is very small in scale, so that we have very weak coupling to the surrounding environment and other atoms, whereas this circuit is inherently microscopic, so we can engineer very strong coupling. Okay. So now we agree that this circuit can behave quantum mechanically. Then we can promote this variables into quantum operators that satisfy these computation relations. Now, however, there is one problem. If we just have linear capacitor and inductor, then we can only build linear harmonic oscillator that has equidistant energy state. So we cannot actually precisely steer the system into a specific state. So we still need some nonlinearity in this device. And fortunately, the Johnson Johnson comes into rescue. So as shown here is a very traditional Johnson Johnson formed by superconductor, insulator, superconductor. And if we add this Johnson Junction instead of the linear inductor, then we can engineer this type of potential and energy spectrum. And these guys are now anharmonic, which means we can now steer the system into the specific state that we want. Moreover, we can couple these atoms or artificial atoms to an ancillar resonator, and we can measure the state of these atoms because the resonance feature of this ancillar resonator is different, corresponding to different energy state of these artificial atoms. And I also want to emphasize that the photon energy of this artificial atom is very small compared to the real atoms. So actually, when we scale up, there should not be any limitation due to the energy concern. Okay. In addition, we can apply a magnetic flux to tune the phase interference of the two Johnson in parallel, which is called a squid. And using that, we can tune the spectrum of this device. However, I want to bring your attention to one fundamental problem. If we can tune the spectrum of this object, then so can the environment. So there is a fundamental trade-off between tunability and the robustness of these artificial atoms. And actually, here are two giants who adopted two different philosophies. On the left, we have IBM, who decided to scale up fixed frequency qubits. And on the right, we have Google, who decided to scale up frequency tunable qubits. The fixed frequency qubits now has coherence times in the range of more than 400 microseconds, whereas the tunable qubits has coherence time in the range of 10 microseconds. But the difference is that the fixed frequency one has very limited interactions, whereas the frequency tunable qubit has very expressive interaction. And that has allowed Google to engineer all of these quantum applications that we have seen, quantum supremacy, quantum phase, quantum phase distribution, blah, blah, blah. Anyway, so I wonder if we can actually have a fixed frequency architecture, but with tunable interactions. And that brings us to this first experiment. So here we have a quantum architecture that is very similar to the one that you find at IBM. Here are the fixed frequency qubits. Here are the coupler, and these are the microwave control lines, and these are the readout resonators, and they are all coupled to a common bus. And I actually brought the kit with me today in case.
All right.
Yeah, so here is the device that is exactly the same that I showed you. Okay, here, pass it along. I also brought a tuba, but there's no need. Okay, so this architecture is very simple. It has very good coherence, and we can actually make these devices and share with any experimentalist who want to play around and find some application with these systems. Of course, the drawback is the expression. We are expressive interaction, so we want to answer the fundamental question: can we overcome the trade-off between robustness and tunability? And I guess you can predict based on this paper with Andrew that we did it. Okay, so let's start from the beginning. What is Heisenberg interaction model? It's simply this is a paradigmatic model that simply contains the XY spin exchange interaction, which means that atoms have an energy exchange coupling with each other. And then there is a ZZ interaction term, which means that the qubits are off resonance, but they still know about each other existence because the frequency of one qubit will depend on whether the other qubit is in the 0 or 1 state. Now this interaction model is the basis for spin-spin interactions. So they are the primitive for quantum application in analog quantum simulations, and also the basis for gate-based algorithms such as swap network and quantum error correction encoding. Okay, and I would like to note that we were inspired by neutral atoms people because recently they have demonstrated that by using laser they can form optical tweezers to move the atoms around very coherently and with very high fidelity. And since the intensity of these lasers are so strong and the atoms are still so coherent, we believe that we can do something similar with the microwave drive to a superconducting qubit. Okay, so what do we have? So here is my artificial atoms, and here's the analog of my laser. When I shine the laser into this artificial atom, the dynamic of this system is described by this Hamiltonian, and that obeys the Schrodinger equations. However, we know that this has to be shown perturbatively in the rest frame, and it is not clear what the solution may look like if we write strongly, increase the write stronger and stronger. Fortunately, we learned about the flow case framework, and the flow case framework simply says that if this drive is periodic with a period t, then the dynamic obeys the flow case equations where in the rest state, the system are in the flow case state and the energy are the flow case energy. And here we show that by changing the right detuning and the right amplitude, we can change the energy of the rest system very coherently. Of course, there's a caveat that the system must be mapped between the bare state and the flow case state in an adiabatic manner. And if we can do that, then we can engineer the Heisenberg interactions in the rest frame between the flow case state, and then we can map back the state to the bare state in order to do single qubit rotation and readout. And this can be represented in this log sphere. So we pause the qubit from the bare state to the flow case state where some interaction occur, and then we shift it back. So in this experiment, we focus on two couple qubits, and here they are represented as the red and the blue spins. And here you can see the junction of each qubit. And our goal is to use these three microwave drives to engineer the XXZ Heisenberg interaction with tunable anisotropy, which is the ratio between ZZ and XY coupling. Okay. Okay, so here we first define the concept about adiabaticity. If there is some adiabaticity, then the rest atom is excited in the rest frame, and then we actually have a finite population in the excited state. So we will form a simple experiment where we drive the qubit off resonantly, and we decrease the ramming time just to see some non-adiabaticity, and indeed we saw some finite oscillations of the excited state, as you see here, when we decrease the ramming time more and more. Whereas for long ramming time, we see very little excitation, meaning that the process must be diabatic. Okay, and we repeat this experiment with different RAM time and different drive amplitude, and we confirm that for stronger drive amplitude, we can simply increase the RAM time in order to keep the system mapping adiabatic. Interestingly, we found that we can perform a shortcut to the adiabaticity technique by doing a power shaping, which is very simple to do, and by doing so, we can reduce the RAM time from 30 nanoseconds, from 60 nanoseconds to 30 nanoseconds, which is significant for us because we want the interaction to happen as fast as possible. So knowing how to map the system from the bare state to the flow case state, we now proceed to realize programmable Heisenberg interactions, starting with the XY interactions. So here we write qubit 1 with the red detune drive, qubit 2 with the blue detune drive, and you know that they can AC stack shift these qubits into resonance with each other. However, now with adiabaticity, the process is very coherent. As you can see, the exchange interaction now manifests as the chevron pattern here. And if you look along this optimal driving amplitude and look at the population swapping, they are very coherent up to 1 microseconds. Okay, and that is for XY. How about ZZ? So by applying two pulses at the same frequency rate, we tune from Q1, we saw that we can tune this ZZ angle by simply changing the rhyming phase of one drive, of this drive here. And this is the result for XY interaction off and XY interaction on. And in both cases, we can tune the ZZ, which means we achieve the full tuning of anisotropy. Okay, so with these iterations, we can now use this simple architecture to study many interesting phenomena as shown. Phase transport, phase transition, and anomalous spin transport. However, for our specific experiment, we were wondering how to benchmark the robustness of the scheme. So one way to do this well is to realize two-qubit gates from the engineer interactions. So here from the exact interaction, we can engineer an I swap unitary. And this is the experimental result. And from the ZZ, we can engineer control Z unitary, and here is the result. And with the exercise, we have the swap. And with this, we believe that the process can be very coherent and have high fidelity. In order to benchmark it without reparation and measurement error, we use cycle benchmarking, which simply consists of interleaving this gate between randomized Pauli matrices. And these are the results. We also measure the reference cycle, which does not contain any two-qubit gate. And by comparing, the red cycle with the reference cycle, we can extract the fidelity of the gate. And yeah, we were very surprised that before our study, it was not possible to realize this gate. But we not only realized that, but we also showed that these operations are highly coherent with high fidelity. Okay, good. What else can we do? So of course, the transmon is not simply a two-level system, but it has many levels. And here we show that the XY interaction can also be realized between Q-tree levels. And here is the specific example where there is a coherent exchange interaction between 1, 1 and 0, 2. And as you see, the process is very coherent. And in order to benchmark the interactions, we use it for this shelving sequence, which basically shelves one of the control state. And with this, we can engineer a control Z dynamics by sandwiching the XY interaction with the control Z in the middle. And this manifests as a CCZ interaction that has a pi phase shift on the target qubit if and only if the control qubit is in the 1-0 state. And this is a very good demonstration of the versatility of the protocol, because in order for this to work, we must have no spectator errors, no spheroid leakage, or unwanted interactions. Okay, and here are the benchmarking results, which show that this is actually one of the best three-qubit gates ever realized. And it was actually the best for a few months until Neutral Atoms paper came out. So here is again the paper that we wrote together with Andrew and Vivek here. And in this paper, we conclude that using our scheme, we can engineer expressive interactions, high fidelity qubit gate, CCZ gate, and also we chart out new directions in control optimizations. Okay, so the first item that I described is the programmable Heisenberg interactions. Now we come back to the drawing table and we look again at the transmon as a qubit, or rather a bosonic system, not a qubit. Why? Because there are many advantages of a high-dimensional system, and people have proposed and studied this system and show that we can increase the computational capacity that open new avenues for quantum error corrections, higher threshold for topological codes, and also more efficient multi-state distillation, so on and so forth, which you can look at in this review paper. And there are also applications in like quantum sensing and quantum communication that I do not discuss here. But the bottleneck is, we ask ourselves again, can we actually effectively engineer a robust and extensive interaction between these qubits, especially XY interactions? So while doing the experiment on the flow case scheme, we realized that a two-body Raman transition can be engineered between any two qubit levels by following this physics. So we know that by parity, we cannot directly write KL to K plus 1, L plus 1. However, if we arrive at a frequency close to the middle of the single photon transitions, then we virtually populate this single photon state. And this represents the two-body Raman transition such that we can actually induce a virtual transition here and here that manifests as a two-body, two-photon transition between KL and K plus 1, L plus 1. This is analogous to the Momo-Sorensen gate study in trapped ion, except that now we have the potential to actually drive at a single frequency and also tune the driving frequency as we wish.
Do you need to suppress the signal condition still?
So this is not populated at all. Yeah. Yes, and it also has to be adiabatic such that you transform this into the rest frame without actually driving anything. And actually in this paper, I will show you in a second. Katik has a very nice way to compare the perturbation theory, when you consider the drive as the perturbation and then the coupling as the perturbation. Yeah, I don't show it, but you can check the paper. So this interaction led us to envision a qubit quantum processor that can be visualized as follows. So here, the qubit can be represented as a non-cyclic gear where we can turn the gear to realize, local rotations. And the two-photon drive can couple both qubits at the same time and drive them rather up together or down together. And here I show you the single qubit rotation. This is the Rabi drive between different levels, which are very coherent. Yeah. And here are the single qubit Clifford benchmarking. And here I want to remark that the lower fidelity that you show for d equal to 4 compared to others is simply because a single qubit Clifford for d equal to 4 contains many more native gates than d equal to 2. Yeah, not just because the native gate is worse. And here the readout results showing that we can couple to an ancilla resonator, and this resonator show different response corresponding to different state of this qubit. And here are the readout fidelity, very high. Okay, so using this, we can actually do initializations and also post-measurement selection. Okay, so here I show you the two-photon transition between 0, 0 and 1, 1 that manifests as a chevron pattern, similar to the flow case scheme, but now this is the double excitation manifold instead of single energy exchange. And here is the interaction between 1, 1 and 0, 0, 2 and 2, 2. So the 1, 1 to 0, 2 is exactly the same interaction that I showed you before in the flow case scheme, because in the rest frame they are shifted and are on resonance. However, if we look at this optimal driving frequency, we see that 1, 1 and 2, 2 still have a very coherent and high fidelity exchange interaction up to microseconds. So we believe that this can have high fidelity. So here we study the optimal driving frequency and also the interaction rate, and we fit it to a very simple model that my colleague at Berkeley worked on, and he showed that the theory fits the experimental data very well with with just taking into account the relevant qubit levels. Okay, so what can we do with this dual bosonic ladder clamping, right? So one thing that comes to our mind is that two-photon driving is very similar to a squeeze drive in bosonic systems, and indeed, so here I plot the effect of two-axis twisting Hamiltonian that have on the qubits. So we climb the ladder and we see we can realize similar effect of this squeezing. So here's the bell state that you are very familiar with. And this is the 2 qubit bell state, and this is the 2 quark bell state. And if I analyze the Husimi Q functions of this bell state, we can see that there is the squeeze along the y-axis, very similar to the effect of this squeezing operator. Moreover, we can also realize the Nguyen state, which is also very important state to perform, sub-Heisenberg limit quantum sensing in photonics. And by also analyzing the Husimi Q function, we show that there is also squeezing, but now this is along the z direction, which is orthogonal to the y directions. So we believe that this can have very important applications for quantum sensing in the future. And okay, maybe Andrew team is also familiar with the cat state by now. And cat state, we can think about them as a simple superposition of microscopic state. And usually people study cat state using bosonic system. However, there also exists a version of atomic cat state that can be realized using spin, and they usually call it atomic cat state or spin cat state. However, usually people increase the size of the cat by including more and more participants, but we believe we can also increase the size of cat using higher levels. So that's what we did. By increasing the dimension of the system, we realized a relatively big cat of 2 quark with a very high fidelity, and also of 3 quark with also very high fidelity. And this is the first experimental implementation of high-dimensional Schrodinger's cat state, at least in superconducting qubits. So why do we care about this cat state, right? Recently, there is a proposal that study atomic Schrodinger cat state in high-dimensional system, and they show that by using high-dimensional state, we can encode the logical qubit into this cat state, which have threshold similar to bosonic cat. So we believe that this is a very promising direction to build up, logical parameter corrections in the future.
Long, for this data, how many photons are in this cat on average?
So, like Q quark has 4 levels, so you can think about it as 4 photons, right? Yeah, so 4 times 3, yeah. So 3 Q quark is maybe 12 photons. And you can compare it to like a single Kerr cat, which 10 photon in the Kerr cat is already a big cat. Yeah. So we believe that this is relatively big. Okay. And I have shown you that we can go up the ladder, but how about in the horizontal direction, right? Because now if we think about it, the 2 photon interaction can be used to realize swap interaction as well. And here we first perform an entangle operation between 2 coupled qubits, and then we try to do some swapping, and we realize some non-local entanglement between the qubit, between Q1, Q3, and Q1, Q4. And this is just a simple population measurement to show that we at least shift the population. Or we can also spread the entanglement into the next qubit to Q3, and now all of the qubits. And we perform quantum state tomography to learn how good of a job we can do. And this is the state tomography of this guy. And the fidelity is 82.7, not too shabby. And this clearly passed the entanglement threshold between qubits. Okay, so here is the paper, and here's the conclusion of the paper. Yeah, you guys can check them out on archive, and maybe we can discuss more if you have any interest in developing in these directions. Okay. And yeah, I just want to summarize the topic that I just discussed. And now I will move on to Foxonium qubits and architecture. So yeah.
Look into the robustness of this cats.
Yeah. You can think, yeah, we can discuss more, but I have not thought much about it, because in order to do this, you also have to say how good of a cat it is, and the fidelity is one concern. Yeah, and also maybe the transmon is not the best candidate to realize it. Maybe there's some other qubits. So you must have know Chong Hong, and this is the chip that he made, and Bing Chang SEM it, and this is the chip that you can also take a look at. Yeah, this is exactly the same chip that I showed here. Yeah, exonium. So this is the exonium. This is the flux coupling line. This is the lump element resonator that you use to read it out. And this is the bus. Yeah. Okay. So let's see. Okay. You know, the transmon is the workhorse in superconducting quantum computing, but it has some certain drawbacks. Of course, we know that transmon is a large capacitor, and that leads us to capacitive loss. Moreover, in studying the qubit, we discovered that transmon has charge sensitivity of higher levels that leads to dephasing, and the low anharmonicity leads to spectral grounding. So we ask ourselves now, if we shunt this junction with an inductor, now we don't need capacitor anymore. There's no charge sensitivity. Can we actually have a better platform? The answer is actually not so simple. And many people have tried in the past, right? So here's the flux qubit, and here's the IF squid qubit. And in both cases, they show that there is a large coupling to a flux noise, so that you actually need to reduce it. And the best way to reduce it is to introduce a large inductance, because inductance scale sporadically with this guy, with the T1 due to flux noise. Again, this happens because you get rid of the island, but you introduce a loop. So when you introduce a loop, you have to care about flux noise. Okay. Now there is a disparity between charge and flux in nature. So here I show the charge fluctuation and the flux fluctuation in nature. So in one case, this scale is square root of IQ over Z naught. Yeah, in the other case, it scales inversely proportional to it. And these two guys are defined by this, phi structure constant in nature, and yeah, this cannot be changed. This phi structure constant is much less than 1. So nature just naturally prefer charge noise compared to flux noise. In other words, we also have more charge fluctuation compared to flux fluctuation, which makes which makes it very challenging to realize large inductance. Why? So let's say we want to make a large inductance, right? The simplest way is that you take a piece of wire, you make a coil. However, this coil has a parasitic capacitance, and that forms, now you see that this is like a resonance structure. So we no longer have like a lump element inductor anymore. So the way to overcome this challenge is that we rely on a piece of superconductor, and the superconductor has a kinetic inductance that is much larger than the geometric inductance. And this piece of superconducting wire can also be emulated using an array of Josephson junctions. Instead of having a continuous phase evolution along the wire, we have a discrete jump of the phase. Okay, so assume that if we can make a very large inductor, what can we do and play? So this is called the fluxonium qubit, and this is defined by roughly this set of parameters. So this EL corresponds to a very large inductance, and this is the typical spectrum of a fluxonium qubit. At flux point around 0.1, the potential is very similar to that of a transmon. You just have state localized in the wells, etc., etc. But when you move to this point, then the potential form local wells, and now the state become disjoint, and they represent the current state flowing clockwise and anti-clockwise around the wires. And at point number 3, you see that you have a hybridization between the two. And at point number 4, the two current states hybridize completely. and the energy of the qubit is determined by the splitting between these two states. And this is very sensitive to the height of this well. So this is the regime that I will discuss next, but you can also operate the qubit in other regime. Okay. So first of all, we try to understand the suppression of dissipation in Boxonium. Here, this is the transition frequency. This is the dielectric loss prediction and quasi-particle loss predictions. On one hand, the dielectric loss scales sporadically with the frequency. So we believe that by lowering the frequency of the qubits, we can lower the effect from dielectric loss. On the other hand, quasi-particle tunneling is nothing else but, a process that can be prohibited by symmetry. And here, this has been shown that by biasing the qubit at the half-plus quantum, this matrix element is completely canceled due to symmetry. So we believe that we can engineer highly coherent qubit. So this is the 3D Boxonium that was done back in 2019 at the University of Maryland. So this is the Boxonium qubit chip, and it is mounted inside of this copper cavity for both readouts and packaging. And here you can see the pin of the resonator sticking out. And this is, when you zoom in, you see the antenna that you use to couple the qubit to the cavity. And this is the small junction and the junction array. And this chain contains about 100 to 200 junctions with an inductor of approximately 150 nanohenry. And this is the spectrum of this typical device. Here we show very good fitting to a simple Hamiltonian with only 3 parameters. So although this circuit contains many ingredients, multiple junctions, etc., its dynamic obeys a very simple Hamiltonian, and we believe we can completely predict its behavior. Okay, so here, instead of this curve that shows lower T1 at low frequency for an RF squid, we show that for Boxonium, when we go to low frequency, the T1 actually become exponentially higher for these qubits and also several qubits at the half-plus quantum. And the difference here is that this one has a very small inductance, and for Boxonium you have a very large inductance. And we conclude that the relaxation times are primarily limited by dielectric loss in the qubits. Not sure where or how, but this provides compelling avenues for other experimentalists to explore, new materials for Boxonium, new superconductor, etc., so on and so forth in the future to further increase the coherence times. There's no fundamental limitation yet. So here I show you the T2 measurement of the Boxonium qubits across the symmetry flux point. And away from the sweet spot, the decay follows a Gaussian profile, which is characteristic of 1/f noisy phasing. And at the sweet spot, it shows an exponential decay, which must mean that there is no flux noise anymore. And by measuring many qubits at the sweet spot, we conclude that T2 primarily scale with T1. If you increase T1, then T2 also increases. So the conclusion is that T1 is the limiting factor, which leads to dielectric loss study. And again, this is the paper. And since then, people have tried different material, and they have increased the coherence time up to more than milliseconds. So yeah, it's a very promising platform. So you cannot do quantum computation with only 1 qubit. So in a following study, we couple 2 qubits, qubit A and qubit B together. And this provides a capacitive coupling of these 2 circuits, as you see here. And although the matrix element in the computational subspace is small, we rely on the non-computational subspace to provide a coupling between these levels. And we know that we can realize a geometric phase gate by arriving at a frequency between these 2 transitions that induce a geometric phase that is different for 10 to 20 and 11 to 21 here. And if we do it well, we can realize pi phase shift on the 1-1 state only. That is equivalent to a control Z gate. And here is the benchmarking result showing very good fidelity, 99.2%. And yeah, back in 2019, it was pretty good. And this is the paper that we reported study. However, that is a 2-qubit experiment, and we also want to explore how good Boxonium can scale up. And yeah, I also did that during COVID, and I wrote up a paper. The conclusion of the paper is that we have very good yield if we combine Boxonium with the Floquet style gate. And also we study the logical error encoding, and we show that the logical error rate can decrease exponentially even if the qubit has relatively short coherence times. So yeah, we hope that there will be effort in scaling up Boxonium. And our work have inspired other groups and companies to study Boxonium. Here are a few examples. These are the recent results from Alibaba, MIT Lincoln Lab, Atlantic Quantum, some group in Moscow, Russia. This is the result from Stanford University, and they all report, high fidelity in single qubit gate and 2-qubit gate. And these are definitely better than Plasmon. And there's also a major effort at Berkeley, of which Andrew and teams are part of, to understand Boxonium and how to scale it up. Good luck. Okay, so to summarize, I have introduced you to 3 different directions that we have both been working on to improve superconducting architecture and technologies. I guess I'm out of time, no?
You have a little bit more time.
Okay. So in the next few minutes, I will discuss noise protected qubits and basically the principle and how we are trying to make it happen. So when we think about errors, we think about how to actually correct it. And the way that people think about correcting quantum error is that we encode information into multiple physical qubits, such that when a local error occurs in one physical qubit, we can actually detect it and correct it. But it is very resource intensive. We know that there is an analogous way to encode quantum information physically into one physical qubit. If we can encode quantum information using a wave function that's spread out across the phase space, if the error occurs at one spot in the phase space, then it does not really dephase the qubit, but rather just affect it very slightly. So, and if these wave functions are also disjoint like this, then there exists no channel for the energy relaxation to occur. So if we can, encode information into, phi 1 and phi 0 here, then the information is preserved from the environment. And one idea is this GKP Hamiltonian, which is nothing else but the sum of 2 cosine of 2 quantum operators that commute up to I. Yeah, they obey this commutation relation. And if we can encode information into this GKP state, as you see, yeah, it will be perfect. And I would like to emphasize that already in their paper in 2001, GKP, these 3 people have already envisioned the way to encode information using hardware, but yeah, not clear how to actually do it. Okay, so in superconducting circuit, we actually can have them. So this is a phase slip element, and this is a double Cooper pair tunneling element. And actually, yeah, they are completely analogous to the Hamiltonian described in the previous slide. And we show that by numerically analyze this system, we can show the GKP state or grid state, if you may, that are protected from energy relaxation and dephasing at the same time. Of course, life is not always rainbows and butterflies. When you make a circuit, there is always parasitic inductance, and parasitic capacitance that form inductor and capacitor. However, here we numerically show that as long as this parasitic effect is small enough, then we still have a reasonably robust encoding in this grid state. Okay, of course, the question is, how to make this circuit element, right? Because they are so exotic. So first, I want to discuss the phase leap element. So now, if we look at junction junctions shunted by a capacitor, the dynamic is described by this Hamiltonian. And in analogy to that, we have a phase leap element in series with an inductor. And this dynamic is described by this Hamiltonian. And incidentally, if we look at the spectrum, they are completely analogous to each other. So here you have the energy splitting that scale with EJ, and you have energy splitting here, scaling up with a phase leap amplitude. So we can conclude that, the phase leap is nothing else but just a small wiggling in a loop that contains an inductor. And people have realized it in the past. But I will not discuss those papers because I don't have time. I just want to show you that we have realized a Blochnium qubit by shunting, or rather, put in series of a very long inductor, very large inductor that we call the hyperinductance, a small junction, which we call the phase leap junction here. And because of this phase leap, we can satisfy the condition that the phase leap amplitude is much bigger than the inductive energy. And here is the on-chip readout resonator that couple to the long chain of junctions. And this is the paper if you want to read more about this technology. Okay, so here is the spectrum of the Blochnium qubit. And of course, we can fit it to this Hamiltonian very easily. And these are the parameters that we extracted. But this is boring. What the interesting part is that we can fit it to the quantum phase leap Hamiltonian. And then from this, you see that in the low energy regime, the Hamiltonian fits very well to this spectrum, showing phase leap amplitude much bigger than the inductive energy. So this makes us believe that we can realize this GKP Hamiltonian. How about double qubit pair tunneling? As you know, in a tunnel junction, there exist multiple harmonics of the cosine phi. So that you have cosine phi, cosine 2 phi, cosine 3 phi, so on and so forth. But the trick is that we need to cancel the cosine phi. And in this paper, they use kind of nanowire with tunable barrier. And here they bias the flux at the symmetric point, and they cancel the cosine phi, whereas the cosine 2 phi is amplified at this flux point. And they show that with using this, they can realize cosine 2 phi. So this is, one method. The second method is that, this is a very recent, actually, theory proposal, not an experiment. And they propose that by using one type of deep wave superconductor with a specific angle, they can suppress the cosine phi tunneling. And only Coopers that tunnel in pairs are allowed across these two pieces of superconductor. And with this, you can also realize a double qubit pair tunneling element. So this is a pretty novel experimental, theory result. Okay, but for our lab, we don't have fancy equipment. We cannot make this element. So we decided to stick to pure superconducting elements. And we know that if we can engineer the potential that is shaped by the junction junctions and the inductance, then we can shape the potential in such a way that the effective particle tunnel is must follow this instantaneous trajectory. Yeah, and it is described by this effective phase phi differential between phi 1 and phi 2 here. And this is pi periodic in phase phi, which is a double qubit pair tunneling process. So we actually did the experiment recently. So here I show you the device, and we actually shunt it with an inductor in order to make the experiment easier due to symmetry. And here in the spectrum, I show you that there is in the cosine phi regime, the period is twice as that of the cosine 2 phi regime, which means that we have realized pi periodicity in this device. And that motivated us to make the grid state qubit. So this is the first implementation. And yeah, we actually have some recent results, which I did not have time to put on to the slides, but we can discuss further. So here we include the phase dip element, and the symmetry allow us to realize the double Cooper pair tunneling. And this is the numerical simulations of the wave function in this circuit, and we show that the wave function form grid state. And yeah, hopefully we have enough result for March meeting, because I submitted abstract and I still don't have result. Yeah, so but we conclude that if everything works according to our prediction, then we can have disjoint wave functions that allow T1 rotation. And we also have the spread of this wave function in the theta 1 and theta 3 phase space. So we have T2 rotations. Yeah, no promise on the number yet, but seems promising. So yeah, I have shown you everything on the slides today. I would like to emphasize that all of our research directions are complementary, and the goal is, again, to realize a simple, robust, resource-efficient architecture where quantum information is conserved very well and also can be exchanged very well between isolated qubits. And we can do this in superconducting circuit because we have a very nice toolbox that people have not really fully utilized to engineer different system, different architecture to study interesting physics. And with that, I would like to just thank my collaborator, my groups, and I would like to motivate people to do experiments. Thank you very much for your attention.
Thanks for a very impressive talk. We can have time for questions.
I think I do need a better picture of you and feedback, but I hope you don't mind.
Not at all, not at all. Yes, Tathagat.
Yeah, thanks for the nice talk. I was just wondering, when you were talking about the flow cake, you said that you're thinking about new directions and control. Could you speak more about that?
So he's actually writing a paper. Maybe you can ask him. So yeah, we are thinking, now we are trying to make things adiabatic, which, adiabaticity is equivalent to slow. People just don't say slow. They just say adiabatic. But, it sounds fancy, but that means slow. So in quantum computing, you don't like slow, you like fast. So how do you make things fast, right? Which means you operate things diabatically. But that means you must understand the spurious things that come from it very well. And if we understand that well, then you can engineer faster interactions. And this is one direction. Like you understand that, you optimize the process so that this is fast and still high fidelity. So that's one of the directions we are thinking. The other direction is, seems like, if you think about it, your flow K qubits is defined by this artificial laser, right? Microwave drive. So if this microwave drive fluctuates, then you have lower coherence because your Hamiltonian is defined by this, laser. So how do we overcome that and characterize that? And is there any thermal effect from that? That's in another direction that we need to study. Yeah, you should ask him more. He's the expert.
More questions? Yes, Peter.
The two chips that you showed us, when they are in the device, they have to be super cooled? Or?
Okay, they are cool devices, but yes, they have to be at 10 milli-K. Yeah, and 10 milli-K.
Okay, and then how many qubits is on these?
So actually the Fluxonium chip is a test device. So, they put many devices on them, but it doesn't matter because they don't talk to each other. What matters is the qubits that you put on that actually can talk to each other. And on the transmon chip, there are only 8. 8 qubits.
But they can all cohere. Or,
Yes, yeah, yeah.
I mean, originally you showed us the hydrogen atom,
yes.
which I sort of understand.
Okay.
But when you talk about these qubits, they don't have anything to do with single atoms, right?
Yeah, so I just want to motivate that, we can think about these circuits as single atoms. Yeah,
But in practice, they are much more complicated and macroscopic.
that's right. Yeah.
Then they have microwaves with which you modulate what happens.
Yeah.
So
Yeah.
is this called photonics? Or I mean, how do you think of these microwaves? Is it
I can think about, like when we think the microwave, we think about classical object, right? But I can say the same thing about light. Yeah, this light is classic. However, if we can isolate this light into the single photon level, then the process is completely quantum. So I can say the same thing about microwave. If I can describe this microwave using, as particle with some energy, then this is completely quantum. So yeah.
So Long, maybe you can show Peter your tuba. Because what they do is they don't have photon detectors usually in these experiments. They have other kinds of amplifiers, and these are really important. And this is an example of it.
Yeah, this is an amplifier which is broken because I just put it in my bag. Yeah, so you put this. The nice thing about superconducting circuit is that everything is commercial. You can just buy this microwave equipment. You put power low enough so that this is in the single photon level. Then the process that happens in the fridge, all of the thermal processes are isolated, right? Like this is very cold. So then we can study single photon effect at the microwave frequency.
And at Berkeley, you have such labs where you actually do the experiments, or?
Yes, yeah.
Love to see some pictures.
I have some picture. I can show you. Should I show it now or?
Why not?
Sure. Okay. So this is actually my job talk, but
wow,
let's see.
So
So this is the Berkeley lab, and you see this is the fridge. Yeah, sometimes I feel like it's more like a dancing club, but because of the light. But this is the fridge, and this is the measurement computer, and this fridge is sitting here. Yeah, and we have like clean room to make the chip and so on and so forth. Yeah, and this is the water system to run the fridge that I have to fix very often. Yeah.
Thank you so much.
Okay, other questions? Justin.
Since you mentioned we want to go fast, is
Yeah.
there any problem with the lower frequencies being more robust in the Smithsonian case?
Yeah. So the problem with the low frequency is that you cannot use rotating wave approximations. And we have realized that yes, the rotating wave approximation completely breaks down at the low frequency regime for the analytical level. However, we found that if we can optimize the right pulses numerically, there's no problem. I just don't know how to think about it analytically in a nice way. Yeah.
But do we have any problems with gate times?
No. Yeah, we can just like make the pulse, shape it, drive it, maybe not on resonance with the qubit, but slightly detune frequency, these kind of things, and we have very good fidelity, at least on the theoretical level. Yeah, it's very good.
Okay, if there are no more questions, let's thank Long again.
Okay, thank you very much.